Bismillahirrahmanirrahim. Hello and welcome to lecture number 3 of Algebraic Topology. In today's lecture, we'll be mainly concerned with the concept of homotopy. But before that, we'll need to review some basic ideas of topology and some basic definition. So, what is topology? So, the beginning of topology is basically related to geometry. But we are concerned in topology with the properties of the object which remains same under continuous deformation. So for example, you can see that this CD under some continuous deformation becomes this bolt, and similarly I can do another continuous deformation to define this object, and similarly I can define a donut and cup and up to so on. So under the concept of topology, or in the eyes of a topologist, all of these objects are the same. So basically we discuss those properties of the objects which remain same under continuous deformation. So topology has many subfields. For example, algebraic topology. So in this course we'll be only concerned with algebraic topology. And so the term topology also refers to a special structure in topology. So let's see how do we define topology in topology. So the structure named topology is defined as the following. So X is a set and sigma is a collection of subsets of X which satisfies the following condition. So X is any set. So for example, I can take X to be 1, 2, 3, and sigma be a collection of subsets of X. So I can take sigma to be 1, 2, 1, 2, 1, 2, 3, up to so on. So this collection, we'll need to add some more elements to this collection, but we will see according to the definition. So the first condition that this sigma should satisfy is that phi and X belongs to the sigma. So in this case, in this example, X is 1, 2, 3, and we can see that this sigma contains the set 1, 2, 3. So, but there is no phi in this sigma, so we need to add empty set into this collection as well. So the second condition that this sigma, this collection of subsets of X, should satisfy is that the intersection of two members of sigma is in sigma. So if I take any two elements from this sigma, then their intersection should also belong to this sigma. So when I take this set 1 and 2, their intersection is phi, so phi is already in the set. If I take 1, 2 and 1, 2, 3, their intersection is 1, 2, which is already in this set. Similarly, if I take intersection of 2 with the set 1, 2, then their intersection is 2, which is once again already in the set. So the second condition is also satisfied by our example sigma. The third condition is the arbitrary union of members of sigma is in sigma. So I can take union of any collection of elements of this sigma, and the union must belong to sigma. So for example, if I take 1 and 2, so their union is equal to 1, 2, which is again an element of this set. So similarly, I can take any other union of these sets and the union belongs to sigma. So the third condition is also satisfied. So the collection sigma with above properties is called a topology for X. So in this example, we have constructed one topology on X. Of course, we can construct many other topologies on X as well. So for example, if I consider sigma to be 1, 3, 1, 3, 1, 2, 3, and empty set. So we can see that X, which is the set 1, 2, 3, with this collection sigma is a topology on X. Okay, so we sometimes denote the topological space X with collection of sets sigma as X sigma, because in the definition of the topology both of these objects are important. So X is the space where we are defining the topology, but the structure of the topology is given by this collection sigma. So the members of sigma are called open sets. So for example, in this example number 1, so let's say this is our example number 1. So in this example number 1, 2 is open. So one open set is 2, but we can see that 2 is no more open in our second example. Okay, so let's say this is example number 2. So 2 is not open. So to be open or not open, of course this depends on this collection sigma. Similarly, a subset F of topological space X is said to be closed if and only if X minus F is open. So in this case our X is 1, 2, 3. So X minus 2 is equal to 1, 3. So we can say that this 1, 3 is closed. Similarly, by taking complements of open sets we can obtain other closed sets as well. But if I take complement of this set, then I will get empty set, which is already there. So empty set is both open as well as closed. And similarly, if I take complement of empty set, then I will get this set X, which is again open as well as closed. So X and phi are open as well as closed. Similarly, we can consider other examples as well. So consider X to be real line, okay, set of all real numbers. We can define a topology on X in the following way. So we can take sigma to be union of open intervals. So what are open intervals? So open intervals of R are of the form, so that is union of subsets of R of the form AB, so where A and B are both real numbers. So the subsets of the form A and B are called open intervals, and the sigma is union or collection of all union of open intervals. So a typical element of this sigma can be written as, so a typical element could be written as, so minus 1 to 0, union 10 to 100, union 500 to 10 raised to power 10. So it's union of 3 open intervals. So this is a typical element of this topology. So this topology is also called usual topology. On R. So in this topology, open sets are union of open intervals and closed sets are union of closed intervals. So for example, a typical closed set is, so a typical closed set. So take complement of the above open set and we will obtain union of closed intervals. So let's see. So what is complement of this? So the complement of this is minus infinity to minus 1 closed, union 0 to 10 closed, union 100 to 500 closed, and union 10 raised to power 10 to infinity. So this is complement of this above set, and this is a closed set, and we can see that of course when it involves infinity, then we can't close that side, so it's union of these closed intervals. So similarly we can find other closed sets as well. So this is an important example of topological space on real line. So closure of a set. Let X be a topological space and Y is a subset of X. The smallest closed set containing Y is called the closure of Y and is denoted by Y bar. So when we say smallest closed set containing Y, so it means it has to be intersection of all closed sets containing Y. So these Fj's is a family of all closed sets containing Y. So for example, consider R with usual topology. So we have already seen that usual topology means the open sets are union of open intervals on the real line. So consider this set Y to be, let's say, this open interval. Now I need to find the closure of Y. So this is our question mark. So according to the definition, it has to be the smallest closed set containing Y, or the intersection of all closed sets containing Y. So what is the smallest closed set containing 0 to 1? So we have already seen that the closed sets are union of closed intervals. So what is the smallest closed interval containing this open interval 0 to 1? Of course, the smallest closed set containing 0 to 1 is 0, 1. So we can say that the closure of Y is basically 0 to 1. Similarly, we can find other examples where we have to find the smallest closed set containing that set. Induced topology is our next definition. We have a topological space and S is a subset of X. Then the topology on S induced by the topology of X consists of families of sets of the form U intersection S, where U is open in X, and hence the open sets in the induced topology on S are given by this. So what we are doing is, so for example, once again consider this usual topology. So with usual topology, where open sets are basically union of open intervals. So consider this set S, which is basically 0, 1 closed interval. Now we need to find what is usual topology, or what is induced topology under this usual topology. Okay, so according to the definition, the open sets are intersection of open sets of X with S. So we know that the open sets of the usual topology are union of open intervals. So what we are going to do is take intersection of open sets from this usual topology with this set S. Of course, this is going to become sets like this. So a typical set will be something like this. So 0 to, for example, 0.5 union, let's say 0.75 to 1. So this is a very typical open set under this induced topology from the usual topology on S. Okay, so similarly we can find other open sets in this induced topology. Okay, so what are the open sets? Open sets are, of course, once again take union of open intervals, because they are the open sets in usual topology with this set S, and you will get sets of this form. And of course, what are the closed sets? So we can easily find the closed sets in this induced topology, because we have to take complements of the open sets, and once again they are intersection of closed sets in this usual topology with this set S. So this is a simple exercise for you to see the fact. So the induced topology is sometimes called relative topology. If S has the induced topology, then S is called a subspace of X. So what is an open cover? So let S be a subset of a topological space, then a cover of S is the collection of subsets Ui of X such that S is contained in the union of that Ui's. If each Ui is open, then the cover is called open cover, and if the indexing set J is finite, then the cover is called finite cover. So let's once again consider our usual topology. So R with usual topology. So let S be a set, let's say 0 to 10. So this is a half open, half closed interval. So it's neither open nor closed in the usual topology. So it has to be any subset of S. So we took this subset which is neither open nor closed. So what is a cover of S? So we can take the following collection. So we can take -1 to, let's say, 1, and we can say 0.5 to 8, and we can say 6 to 11. So these three open sets, let's say this is U1, this is U2, this is U3. So S is definitely contained in U1 union U2 union U3. So we can say that this U1, U2, U3 is a cover of S. So since all of these three U1, U2, U3 are open sets, so we can say that is an open cover of S. And if the indexing set J is finite, then the cover is called a finite cover. So in this case, the indexing set J is equal to 1, 2, 3, because there are only 3 elements in the cover. So we can say that this indexing set J is finite. So that's why we can say that this is finite open cover of S. So U1, U2, U3 is finite open cover of S. So similarly we can find other examples. So for example, we can find examples where this indexing set J is not finite. So for example, if you want to find open covers of R, so we can find a cover which is not finite. Okay, so we can find open covers, many open covers which are not finite, and similarly we can find covers which are not open, etc., etc., etc. Our next definition is the definition of continuous function, which is very important when we are discussing topological spaces. How do we define it? So in most of the books, this definition, which we chose to be as a definition, is written as equivalent criteria, and the main definition is written as this. So due to its simplicity, we took this as our main definition of continuous function. So a mapping F from topological space X to Y is continuous if for every open set U of Y, F inverse U is open in X. So for example, so let's say this is X and this is my space Y, and this is this shaded area, let's say, is open in Y. So let's say this is U in Y, which is open. So the inverse image of this is this collection, so this shaded area in X. So if for U open, this inverse image is open. So if this happens for each and every open set in Y, then we say that this mapping is continuous. So let's consider some examples. So let's consider a function from R to R. So I'm taking R, this R under the usual topology, and this R under the usual topology. So define this function F in the following way. So that's right, I'm taking this F to be identity function. So if I take any open interval in this Y, so in this case X and Y are equal, but if I take an open set in this codomain, so let's say my open set is AB, so this is my U, which is contained in Y, which in this case is R. So what is F inverse of U? So of course this is identity, so F inverse of U, which means F inverse of the open interval AB, is basically AB, which is open in X, which once again is equal to R in this case. So similarly, if I take inverse image of any open set in Y, then it will be open in X. So we can say that F is continuous. So let's consider another example of a continuous function. So consider F from topological space X sigma 1 to topological space X sigma 2. So where X is equal to 1, 2, 3, and sigma 1 is collection of open sets, so 1, 2, 1, 2, 1, 2, 3, and 5. Similarly, we can take sigma 2 to be another collection of sets 2, 3, 2, 3, 1, 2, 3, and phi and X. So we can see that this X under this collection of sets, subsets of X, is a topology, and similarly the same set X under this collection of subsets of X is topology. So define this F in the following way. So F of 1 is equal to 2, F of 2 is equal to 3, and F of 3 is equal to 1. So we can observe that this F is just a permutation of X. So let's see if this F is continuous or not. So basically we have to take open sets from this topological space and see their inverse images, and if the inverse image of each and every open set is open in this input space, then we can say that F is a continuous function. So here this 2 is open set, and the inverse image of 2 is basically 1. Okay, so the inverse image of 2 is 1, so we can say that inverse image of 2 is again open. Similarly, what is the inverse image of 3, the inverse image of 3 is 2, which is again open in our input space. So what is the inverse image of 2, 3? So the inverse image of 2 and 3 is 1, 2, which is once again open. Inverse image of 1, 2, 3 is 1, 2, 3, again open. Inverse image of 5 is 5, which is again open. So we can say that f is continuous function. Similarly, we can consider another example of a continuous function. Consider f from R under usual topology to R under usual topology, defined in the following way: f of x is equal to x square. So we can see that this f takes open sets from this R to open sets of this R. So inverse image of every open is open again. So this is a little exercise for you to check that the inverse image of open are also open. So I'm going to do a typical case. So f inverse of, for example, 0, 1. So we can see that the inverse image of 0, 1, so 0 is not included, so this is going to be a -1 to 0 union 0 to 1. So the inverse image of 0 to 1 is this. So we can also see this by observing the graph of this function, which is a parabola. So I took this 0 to 1 open interval, so we can see that these values are obtained when we take -1 to 0 and 0 to 1. So the inverse image of 0 to 1 is these values. So similarly, we can find inverse images of other open sets, and we will see that there are open sets in R in the input space, so that's why f is continuous function. So in general, polynomials from R to R under usual topology are continuous functions. So polynomials are continuous functions. So next we have some equivalent criteria for continuity. So as I said earlier in most of the books, so this criteria is taken as the main definition. So just like open sets, we can also do the same definition for the closed set. So a map f from x to y is continuous if and only if inverse image of every closed set of y is closed in x. So most of the time we'll be using our main definition, so this equivalent criteria and this equivalent criteria. So we'll rarely be using these two equivalent criteria. So next definition is homeomorphism. So we also discussed this when we were discussing the categories. So I told you earlier that when we are discussing the category of topological spaces, our morphisms are basically continuous functions. So homeomorphism is basically equivalent of isomorphism of groups. So here we are saying that as a topological spaces they are equal. So if there exists homeomorphism between two topological spaces. So what is a homeomorphism? A homeomorphism or a topological mapping between two topological spaces is basically a function which satisfies the following condition. So f has to be continuous, f has to be bijective, and f inverse has to be continuous. So we can find many examples of homeomorphism. So for example, starting from simple examples, so f from usual topology to the usual topology defined in the following way. So identity. So we can observe that f is continuous, also f is bijective, also f inverse is continuous. So it's a very simple example of a homeomorphism. So R under usual topology is homeomorphic to R under usual topology. So let's go to some non-trivial examples now. So any two open intervals on R are homeomorphic. So for example, let AB be one open interval and CD be an other open interval. So consider the following function from the open interval AB to CD defined in the following way. So it is a homeomorphism because in this case, so A and B are numbers, C and D are numbers. So in this expression you can see that this is going to be a number, this is going to be a number, and A minus B is going to be a number, and this number will not be 0 as long as A is not equal to B. So we can say that A is not equal to B is one of our condition. So under these conditions we can see that this h of x is just a polynomial, so polynomial of degree 1. So we have observed that polynomials are continuous functions, so this h of x is a continuous function. And we can also observe that since it's a linear function, so it is also a one-to-one and bijective function. So when I'm saying that it is linear, so it means that its graph will be a line in R2 plane, because this is AB, which is subset of real line, okay, and this is CD, which is again subset of real line. So this is C, this is D. So since this is a linear function, so it will be something like this, it will be a line. So of course we can observe that this is a bijective function. And next is the third condition is its inverse should be continuous. So how to find inverse of such functions? So just replace this h of x with x and this x with h of x, and you will find its inverse. Or let k of x be inverse of h of x. So how to find this k of x? So we can just replace this h of x with x and replace this x with k of x, and now find the value of k of x. C minus D plus AD minus BC divided by A minus B, A minus B. So we can find k of x in the following way: A minus B into x minus AD minus BC divided by C minus D. This is equal to k of x. So once again observe that this k of x is once again a linear function, because these are all numbers. AD minus BC is a number, A minus B is a number, C minus D is a number, and once again we have another condition that C should not be equal to D. So it's a linear function, so it's bijective, but in this case we just need to check its continuity. So as a polynomial it is a continuous function. So h of x is continuous, it is bijective, and its inverse is continuous. So we can say that this function h defined in this way is a homeomorphism from the open interval AB to CD. So we can say that any two open intervals are homeomorphic on R. So any two triangles in plane are homeomorphic. So in fact for two fixed triangles there is a unique affine transformation of the plane which maps the first triangle to the second. So what is an affine transformation? We'll be discussing them in a detailed way in our further lectures, but for the time being we can just say that it's a transformation which is a composite of a linear transformation and a translation. So we have already seen that what is a linear transformation, and a translation is just adding a vector to the application of this transformation. So basically what we are saying is A of x vector is just equal to some linear transformation, let's say t of x and translation. So this vector B is translation. So apply this t on this vector and add this translation to this application of the linear transformation. So in general this is our affine transformation. So there is a unique affine transformation taking one triangle to the other. So let's say this is our plane, and this is one triangle, and let's say this is another triangle. Then there is a unique transformation, affine transformation, taking one triangle to the other triangle, and so this will define a homeomorphism between these two triangles. So definitely when we will be discussing this affine transformation, then after that you will be able to see that why these affine transformation, in this case they will be invertible and the inverse is also continuous, and why this affine transformation is a continuous function. So next definition is compact. So a subset S of X is called compact if every open cover has a finite open subcover. So to be honest, it's a very difficult definition to apply. So the meaning of the definition is very simple. If every open cover has finite open subcover. But when we want to check that some topological space or some subset of a topological space is compact, then we always need to apply some equivalent criteria. So these are the equivalent criteria or some important results when we are trying to check that some subspace is compact or not. So a closed subset of a compact space is compact. Secondly, if X and Y are topological spaces, then X and Y are compact if and only if X cross Y is compact. And thirdly, and the most important result on the compactness is the result by Hein-Borel, and it's also called Hein-Borel theorem. So a subset of Rn is compact if and only if it is closed and bounded. So according to this result, if I want to see that what are the compact sets of R, for example, then they have to be closed and bounded. So closed means they have to be union of closed intervals, and bounded means they have to be bounded. So for example, if I take minus infinity to 1, it is closed but it is not bounded, so not compact. So we can easily say that it is not compact because this is if and only if condition. If it is, it has to be closed as well as bounded if it is compact. If it is if one of the condition of closed and boundedness is relaxed, or in this case this is not bounded, so it is not compact. So similarly 1, 2, it is a closed interval which is bounded, so it is bounded between the two numbers, for example 1 and 2, so that's why it is closed and bounded, so it is compact set according to Hein-Borel theorem. Okay. So continuous image of a compact topological space is compact. So it's a very deep result. So it says that compactness is a topological invariant. So if we have a topological space which is compact, and when I take its continuous image, so continuous image means, so for example f is a continuous space from, so for example f is a continuous function from x to y, and if x is a topological space, then f of x, which lives inside y or which is subset of y, is also compact. So this means that compactness is a topological invariant. Our next definition is connectedness. A topological space is connected if X is not union of non-empty disjoint open sets. So the interval a b, which is a closed interval, is connected because we cannot write it down as union of two open sets, union of two disjoint open sets. But we can consider another example which are not connected. So for example, consider this topological space minus 10 to 0 union 0 to 100. So it's union of two open intervals, and these two open intervals are disjoint. So we can easily observe that this topological space can be written as union of two disjoint open sets. So we can say that it is not connected. So similarly we can find other examples which are not connected. So once again in this case we have some equivalent criterias. if X and Y are topological spaces, then X cross Y is connected if and only if X and Y are connected. A continuous image should not tear a topological space into pieces. That is, continuous image of connected space should be connected. So once again, what is a continuous image? So if we have a topological space, then its continuous image make continuous changes into the topological spaces. So so most of the time topology is also called rubber sheet geometry. So which means that if I have an object made of rubber, then the operations that I can do with that object made of rubber are basically continuous deformations, or its continuous images. So I'm allowed to basically stretch it, I'm allowed to bend it, but I'm not allowed to tear it down, or I'm not allowed to glue some things to it. So as long as I'm stretching and bending this rubber sheet object, I'm basically making continuous image of the object. So under this continuous image, so we can observe that if I have a connected object, then under the continuous image, this connected object should remain connected, and because we are not allowed to tear it down under the continuous image. So our next theorem, it says that continuous image of a connected topological space is connected. So we can say that connectedness is a topological invariant. So once again, it's going to be a very important factor in our next discussions, that the properties which are topological invariants are very important for many reasons. So the maximal connected subsets ordered by inclusion of a non-empty topological space are called connected components of the space. So for example, if I have a topological space, for example a union of these three open sets, then this is basically a connected component, this is another connected component, this is another connected component. Of course, if I have one big topological space which is connected, then there is only one connected component, which is the topological space. But if it is not connected, then we can write it down as union of connected components. So in our previous example from -10 to 0, union 0 to 100. So in this example, it is not a connected topological space. So when I'm saying it's a topological space, it means that I'm taking this S as a subset of R, and I'm taking induced topology from R onto this subset, or induced topology or relative topology. Okay, so this set S is a topological space under this induced topology. So it is not a connected space. So if it is not connected, then we can write it down as union of connected component. So we can observe that this open interval is connected component. Okay, so it cannot be written as union of two open sets. So this is our first connected component, and this is our second connected component. So this disconnected topological space S has two maximal connected subsets. So -10 to 0 and 0 to 100. So to show that X and Y are homeomorphic, we need to find a homeomorphism between them. Of course, what is homeomorphism? We need to find a function f which is continuous, bijective, and f inverse is continuous. But if we want to show that two spaces are not homeomorphic, we need some topological invariant. Okay, so of course this is one of the importance of our topological invariants. So in fact we show that some carefully chosen topological invariant does not remain same in two spaces. So for example, if I have one topological space which is the shape of this X, and we have another topological space which is the shape of this Y. So using this result, so if f from X to Y is homeomorphism, then X minus X is homeomorphic to Y minus Y. So if we have two topological spaces which are homeomorphic, then taking one point out from this set X, that space should be homeomorphic to taking Y and then taking out f of x from this y. Okay, so if, for example, this space x is homeomorphic to this space y, then according to this result, if I take out this central point of intersection, which is named as x naught, then this space should be homeomorphic to, by taking y out this f of x naught. Okay, so in this case, this space x, so if I take this point out, then this space x minus x naught, so it is disconnected. So this space x is connected, but then this space x minus x naught is disconnected, and it has four disconnected or four connected components. Okay, so this is first, this is second, this is third, this is fourth. So it has four connected components. Okay, so but what about y minus f of x naught? So y minus f of x naught has three connected components. So in this case, they will be something like this. So 1, 2, 3. So there are three connected components of y minus f of x naught. So of course you can say that if I vary the image of x naught, so if I vary the image of x naught, so for example, if I take the image of x naught to be this f of x naught, then in this case the connected components will be just two. So first component will be this, and the second component will be this. So something like this. So first component and second component. So which is still which is lower than 3. Okay, so the point is, if I take images of connected components, then I should get connected components, because connectedness is a topological property, and a continuous image of a connected space is connected. So this x minus x naught has four connected components. So the image of this first connected component 1 should be a connected component. So image of this connected component 2 should be a connected component, and the image of this connected component 3 should be a connected component, and similarly the image of this fourth connected component should be also a connected component. So we should get four connected components under the image. So when we are mapping x to y, so I should get four connected components. But in this case, we can observe that if I take f of x naught to be any point on this y, then I can't get more than three connected components. So which means that according to the topological invariance of connectedness, I can say that this space x is not homeomorphic to this space y. So let's consider another example. So take this set S to be collection of complex numbers with their mod equal to 1, and take this interval 0 to 1, which is half open, half closed interval, and define this map from 0, 1 to S in the following way: f of t is equal to e raised to power 2 pi I t. The function f is continuous because we know that this is exponential function, and is bijective as well, but the inverse of f is not continuous. So we have two ways from here. So one way is try to find the inverse of f, and then try to see that why this is not a continuous function, or we can just use the invariance of compactness and connectedness to see that why this is not true. So the inverse image of f is a function from this set S to 0 to 1. Now from Hein-Borel theorem, we know that a subset of R is compact if and only if it is closed and bounded. So by Hein-Borel theorem, this subset of R is not compact. But this S as a subset of R2, so this is basically a circle in R2. So this circle is basically closed as well as bounded in R2, so we can say that this S is compact. Okay, so is compact by Hein-Borel theorem because this is closed as well as bounded. So if F inverse is continuous, then we know that the continuous image of a compact set is compact. So the F inverse of S should be compact. But we know that this inverse, F inverse of S, is not compact because 0, 1 is not a compact set by Hein-Borel theorem. And this F inverse should also be bijective as well. So in other words, the image F inverse of S should exactly be equal to 0, 1 semi-open interval. So according to the invariance of compactness, we can say that there is no such F inverse which is continuous, because if it is continuous, then F inverse of S should be compact, which is not true. So similarly, we can also use the invariance of connectedness as well. So by taking one point out from the circle, so let's say I take this point out from the circle, and if I take some other point out from this interval, so let's say this is 0, 1 interval on this real line. So if I take this one point out, then we can observe that after taking this one point out, now this is not a connected set. But after taking this one point out from the circle, it is still a connected set. So we can see that according to the result that we just used to show that these two spaces X and Y are not homeomorphic. So using this result, if F from X to Y is homeomorphism, then X minus X is homeomorphic to Y minus F of X. So if this circle and this interval are homeomorphic, then S minus this point should also be homeomorphic to 0, 1 minus this point. So which is not the case. Why this is not the case? Because this circle is connected and its image is not connected. So similarly, we can use other arguments using connectedness and compactness to show that these two spaces, that is the circle and this semi-open, semi-closed interval 0 to 1, are not homeomorphic. So using connectedness argument, we can see that R is not homeomorphic to Rn for n greater than or equal to 2. So what is the simple argument? So the simple argument is, if I have a real line and if I take one point out from the real line, then it becomes a disconnected space. But this is not the case, for example, in R2 and R3. If I take one point out from R3, then it still remains a connected space. And similarly, if I take one point out from R2, then it still remains a connected space. So using these arguments and using invariance of connectedness and compactness, we can see that R is not homeomorphic to R2, R3 and Rn for n greater than or equal to 2 in general. So in general, Rn is not homeomorphic to Rm. So this result is not very easy to prove, but we can also use algebraic topology to prove this result. So we will see that later in this course. So using homology and other machinery, we can prove that this is the case. Okay. Let's consider another example of spaces which are not homeomorphic. So a sphere S2 in R3 is not homeomorphic to a torus. So why this is the case? So using this theorem, the Jordan curve theorem, let C be a simple closed curve in the sphere, which means that C is a subset of S2 which is homeomorphic to a circle. So for example, I can consider, for example, this simple closed curve. So then the complement of C has exactly two connected components. So this is the curve C and its complement has two parts, so the inside part and the outside part of the sphere. So it has two connected components, but if I take a simple closed curve on a torus, then it is still connected. But on sphere, if I take a simple closed curve, then it divides the sphere into two disconnected parts, and so basically it makes the sphere into union of two connected components, but if I take a simple closed curve on a torus, then it still remains a connected space. Our next section of today's lecture is homotopy. So the main idea of homotopy is replace a continuous function with another continuous function which is obtained after continuous deformation. So for example, if I have a function f0, so let's say this is the function f0, so this is the graph of f0. So of course in different spaces the graph of f0 will be different, but let's consider f0 is given like this. And we have another function, let's say f1, so represented by this curve. Let's say this is the function f1. So f0 is homotopic to f1 if we can continuously deform this f0 into f1. Okay, so mathematically speaking, if x and y are spaces and if f0 and f1 are continuous maps from x to y, then f0 is homotopic to f1, denoted by f1 homotopic to f1 if there is a continuous map f from x cross y, I to y. So here basically I is equal to 0 to 1 closed interval, such that f of x is 0. So this is the function f of x 0, so which is equal to f of x, f0 of x, and this is the function f of x1, which is equal to f1 of x. So such a map is called homotopy. Okay, so one often writes f from f0 to f1 or f0 homotopic to f1 if one wished to display a homotopy as well. So what's really happening? So for example, if we consider this f of x t, and we know that if it is a homotopy from f0 to f1, then when I take t is equal to 0, then I should get f0, and if I take t is equal to 1, then I should get f1. So consider this t as time. So starting from time t is equal to 0, we have this function, and when we move with time, then this function is basically deforming, and it's becoming, and it's taking its shape into f1. So after time t is equal to 1, we have this function f1. So any function which is in between these two functions, or for example at time t is equal to let's say 0.5, this is an intermediate function, which is the function at time t is equal to 0.5. Similarly, if I take some other time, let's say 0.75, then I will get some other function. So let's say this is t is equal to 0.75, and according to each and every point between 0, 1 closed interval, I will be getting functions which will be between f0 and f1. So the end result is we start from f0 and we continuously deform our function to f1. At time t is equal to 1, we have f1. So in between these two functions and at any time we have some other functions which are basically intermediate functions. So if we have a homotopy from f0 to f1, so this is our function f0 and this is our function f1. So consider this function ht from x to y defined by ht of x is equal to f of xt for x belongs to capital X. So as we discussed earlier, at any time t, so it is going to be a continuous function from x to y. So let's say this is time 0.5, so this is h 0.5. Similarly h 0.75, similarly h 0.25. So these are all continuous functions from x to y. So once again a continuous function from x to y. But the point is, what is h0? So h0 is f0, and what will happen when t is equal to 1? We should approach, or we should get this function f1. So let's consider some examples of homotopic functions. So consider this function f from S1 to C. So S1 is basically a circle in R2, and C, we can consider this C as a plane. So it's a function from R2 to R2. So of course we can't sketch its graph in R3 because its graph will be in 4 dimensions. So we can say that this function, which is defined by f of z is equal to z, which is identity function, is taking this circle to this circle. So this is the domain space and this is the range space. Okay, so in the domain it takes points of the circle and it gives me point in the range space. So let's define another function g from S1 to C, given by g of z is equal to 2z. So once again, what is this function g doing? So it is taking points of this circle S1 and it's giving me twice the points. In other words, the image of g is collection of these points. So this is the image of g, the outside circle and the inside circle are the images of f. Okay. Now if we want to show that these two functions are homotopic, so we need to find a function f from S1 cross I to C such that this circle is deformed into this bigger circle. So at time t is equal to 0, I should have this inner circle, and at time t is equal to 1, I should have this outer circle. Okay, so let's see if we can define such a function. So define f of zt is equal to 1 plus tz. So in this case we can see that when t is equal to 0, then what is f of z0? So for t is equal to 0, this is z, so which is equal to f1 of z. So the inner circle or circle of unit radius. So what is f of z1 at time t is equal to 1? So this is becoming 2z, which is equal to g of z, so which is the outer circle. So at time t is equal to 1, we have at this outer circle. So of course for any intermediate value of t, so for example z.5, we will have some intermediate circle. Okay, so my drawing is not good, so let's just assume that this is a circle. So this is f of z.5, so it's a circle with radius 1.5. So similarly, we can also observe that this function f is continuous map. So all of these three conditions are satisfied, so we can say that capital F from S cross I to C is a homotopy, or in other words, we can say that f is homotopic to G. So let's consider another example, but before doing that example, we need the definition of a convex set. So we have already done that in our previous lectures, but let's just remind ourselves. So what is a convex set? A subset X of Rm is convex if for every pair of points x, y, the line segment joining x and y is contained in X. So in other words, if x, y belongs to X, then this is the line segment joining x and y, so where this I is equal to 0, 1 closed interval. So this line segment, if it is contained in X for each and every value of t, or in other words, for each and every pair x and y, the line segment is contained in X, then we say that this is a convex set. So once again, consider this example. Of course this is not a convex, because if I take this x and this y, then the line segment is not contained in this set. Similarly, consider this circle. So this circle is not convex because this circle is collection of all points on this curve, but if I take one point and another point, then the line segment, so 2 points of the line segment are contained in the circle, but any point of this part, so this part, any point from this part is not contained in the circle. So we can say that circle is not convex. Similarly, we can see that a sphere is not convex, and similarly we can go to higher dimensional spheres or n spheres. So what is an n sphere? So n sphere is collection of all points in Rn plus 1 such that x1 square plus x2 square plus xn plus 1 square is equal to 1. So we can see that when I take n is equal to 1, then it will be basically a circle in R2, and if I take n is equal to 2, then it will be a sphere in R3, up to so on. So we can say that this is an n sphere which lives in Rn plus 1. So as I said earlier, that these n spheres are not convex. So these are not convex due to the same reason as we discussed for the circle. So let's discuss another example. The n disk Dn so is a set of points of Rn satisfying this condition. So x1 up to xn such that x1 square plus x2 square plus xn square is less than or equal to 1, or we are discussing we are taking collection of all points whose distance from the origin is less than or equal to 1. So of course when we discuss R2, then this set is going to be a unit disk, so collection of all points inside this unit circle. So we can observe that if I take one point and another point, then the line segment joining them is totally contained in this D2. Okay, so similarly we can observe for other pairs of points in D2 that the line segment joining them is always contained in D2. So D2 is convex. Similarly we can see that D3 which is sphere and all of its inside points, so basically it's a solid sphere, is also convex due to the same reason. If I take any 2 points, then the line segment joining them is contained in the sphere. So it is basically, so Dn, the n disk, is convex set for every n. Okay, so let C be a convex set, and let Fg be continuous functions from x to c. Then f and g are homotopic. In fact, there exists a function f from x cross I to c defined in the following way. So f of x t is equal to 1 minus t f of x plus t g of x. So observe that f of x 0 is f of x. Of course, when we take t is equal to 0, then we will get, okay, so f of x 0, so 1 minus 0 is f of x, and this t is 0, so it becomes plus 0 into g of x, so which is equal to f of x. Similarly, if I take x1, then this is 0 f of x plus 1 into g of x, which is equal to g of x. Also f of xt is a continuous function. So what's really happening here? So if I have a convex set, so for example take this set, so we can see that it is a convex set. If I take any 2 points from C, then the line segment joining them will also be contained in C. So it's a convex set. Okay, so f is a function. So let's say this is my space x. X need not to be convex. So let's say this is my function f of x. Okay, so these are the image points, and let's say these are the image points g of x. So what are the strategies? So how we can construct this f of xt? So what we are doing is basically I'm taking this point f of x, and I'm taking this point g of x, and I'm following the line segment joining this point, and I'm approaching this point. Similarly, for any x naught, this is f of x naught contained in C, and this is g of x naught contained in C, and I'm following this line segment joining f of x naught and g of x naught, and I'm approaching this g of x naught. Similarly, so I am basically following the line segments joining points of f and points of g. So basically after following these line segments, so I will approach G, and all of these line segments are contained in C because C is a convex set. So using convexity of the C of our range space, we can construct a homotopy from one function to the other function. So let's consider another example of a homotopy. Let f and g be functions from x to Sn, and these are two continuous functions. Now basically the range space is Sn, n sphere. Okay, so we are imposing one condition, that f of x is not equal to minus g of x. Okay, so in other words, what we are trying to say that is if this is f of x, okay, and its antipodal point, so antipodal means its exactly opposite point on the sphere is minus f of x, okay, but this minus f of x is not equal to g of x. Okay, so similarly, if this is f of x naught, then this is minus f of x naught, but we are saying that this is not equal to g of x naught. So we are saying that f of x and g of x are homotopic in this case under this condition. So the only condition we imposed on this f and g are that they are never antipodal points. So antipodal means this is f of x naught, this is minus f of x naught, so this minus f of x naught is not equal to g of x naught for each and every x naught. So let's define this function f of x t, defined in the way 1 minus t f of x plus t g of x, 1 minus t f of x plus t g of x. So observe that it is more or less the same function, but we are defining this value by its magnitude. So when we are defining this value by its magnitude, so in other words we are saying that this output is going to be points on the sphere, because if f of x and g of x are points of Rn plus 1, because this is the space where Sn lives. Okay, so 1 minus t f of x plus t g of x are going to be is going to be a point of Rn plus 1, and I am dividing this point by its mod by taking it as a vector of Rn plus 1. So if I divide a vector by its mod or norm, then I get a unit vector. So if it is a unit vector, then it must live on Sn. Okay, so since f of x is not equal to minus g of x, so that's why this denominator is never going to be 0. So now we can easily observe that if I take t is equal to 0 in this function, so when t is equal to 0, then the numerator becomes f of x and the denominator becomes f of x mod. So why f of x mod is 1? Because f is a function from x to Sn, and the image f of x is a point on the sphere, so its mod or norm should be equal to 1. And similarly, using the same argument, we can see that f of x1 is equal to g of x. So what is this function actually doing? So if I have f of x and let's say if I have g of x on a sphere, then there is a unique big circle. Okay, so there is a unique circle passing through them. Okay, so now I can follow. So basically what this function is doing, that I'm following the shortest path. Of course, if this is f of x and this is g of x, then there are two paths are along this circle, but I'm following the shortest path and I'm approaching this g of x. Okay, so similarly, if f of x is a function from x to Sn, then f of x should be a collection of points on this Sn, and g of x should be also a collection of points on this Sn, but for each x, f of x and g of x are joined in this way. Of course, this is an example of S2, but the situation will be similar for n sphere or higher dimensional spheres. So our last result of today's lecture is that homotopy is an equivalence relation on the set of all continuous maps. So what is an equivalence relation? It's a relation which is reflexive, symmetric and transitive. So let's see why this function, why this relation is reflexive. So reflexive means if I have a function f, then is it homotopic to itself? Of course, this is homotopic if I take the homotopy f of xt is equal to f of x. So for t is equal to 0, it is f of x. For t is equal to 1, it is f of x, and it is continuous as well because f is continuous. So why this is symmetric? So it is symmetric because if we have a homotopy f from f to g, now we want to show that if f is homotopic to g, then there is a homotopy from g to f as well. So let's define a homotopy g of xt which is equal to f of x1 minus t. So in this case, observe that, so what is g of x0? So which is equal to f of x1. So what is f of x1? So if this is homotopy from f to g, then f of x0 should be equal to f, and f of x1 should be equal to g. So if we define g in the following way, then g of x0 is equal to g, and g of x1 which is equal to f of 0. So 1 minus 1, sorry, f1 minus 1 is 0, so f of x0 is equal to f. So similarly, we can see that if capital F is continuous, then this g is continuous. So if f is homotopic to g, then g is homotopic to f. So the next we have to show that it is transitive. So for transitivity, we have to show that if f is homotopic to g using homotopy, for example, f, and g is homotopic to, let's say, h using homotopic, let's say, capital G, then we need to show that, okay, so to show that f is homotopic to h. Okay, so we need to find a homotopy h of xt, okay, such that h of x0 is f and h of x1 is h, and they are also continuous. So let's define h of xt in the following way: f of x 2t, okay, so where t varies from 1 by 2 and 1, and similarly g of x 2t minus 1, where t varies from 1 and 1 by 2. So what is h of x0? So in this case, h of x0 is so 0, sorry, this is 0. So 0 belongs to this interval, so which means that f of x0, so f of x0 we know that is f. Similarly, what is h of x1? We can see that 1 belongs to this interval, so if t is equal to 1, then g of x1. So what is g of x1? So we can see that g of x1 is h. Also, there is only one point where these two components of this piecewise function are overlapping, so that's the point where t is equal to 1 by 2. So when t is equal to 1 by 2, we have f of x. So when t is equal to 1 by 2, we have this f of x1, and when t is equal to 1 by 2, we have g of x0. So what is f of x1? It is equal to g, and what is g of x0? It is equal to g. So when t is equal to 1 by 2, we have g, which is a continuous function. So on the overlap, there is no problem, and since g, f, g and h are all continuous function, so that's why we don't have any problem. So on the overlap, they are also continuous, otherwise f is continuous and g is continuous, so h of xt is continuous. So we have a homotopy from f to h, so it is also transitive. So we can say that homotopy is an equivalence relation, which means that if we fix our spaces x and y, then set of all continuous functions from x to y can be divided into classes. So what are the classes? Where each class contains homotopic equivalent functions. So we will continue with the discussion of our homotopy. So in particular, we will be considering the h-top or homotopic category. So in this particular example, we can see that a cup is homotopic to a donut, So of course we'll not be doing the mathematical details of this example, but this is just for your illustration that that's how one space can be continuously deformed into another. So that's why in this case this cup is homotopic to this donut. So this is the end of the lecture. Thank you very much, and Allah Hafiz.